Starting today until the end of this semester or until the end of this class, we're going to be talking about, I guess, digital. We're going to introduce digital transmission. There are a few lectures on it. There's not much time, so my hope is really just to give you basics. And then we have a separate course that we call digital telecommunications or digital communications that covers nothing but digital. But here, based on what we've covered so far in analog, we have a pretty good set of tools that will allow us to at least explain how digital works. So, so let me just start here by saying digital communication. First thing that, since this is a huge subject, the only hope we have is kind of to limit the scope. And the first scope limitation is going to be the channel. We're going to consider communications through AWGN. So our channel is going to be AWGN channel. AWGN stands for additive white Gaussian noise. Now, you have now enough background to understand every one of these adjectives here. Additive means it tells you what kind of impairments does this noise produce to your signal. It adds to the signal. White refers to its power spectral density, its constant power spectral density in the frequency domain. Gaussian, it is Gaussian in the amplitude domain. It is normally distributed with zero mean and some standard deviation. Noise is just essentially to tell you that this is a random process that we're dealing with. So just like in the case of the analog communications, let me first draw a block diagram so that we can see what is on the subject of this study and kind of address those blocks in the block diagram. So just like in any communication system, we're going to have here a source. Then there will be a process that I'm just going to refer to analog to digital conversion. This is by no means, I guess, trivial process. There's sampling and quantization here, and there's quite a bit to be said about sampling and quantization, how you sample and how you quantize. But we're going to assume that we're not going to study this in this course. We're going to actually start from this point on. And so we're going to assume that we're given a bunch of numbers. So this is digital information. That we have a bunch of numbers that are passed to our communication system. You cannot send numbers, over the communication system. Our world is analog. So the first thing that happens is these numbers are mapped into analog waveforms. So digital info to analog waveforms. That's the mapping that is really what we refer to as modulation, right? You would take these digital bits or numbers, and you would have some carrier here whose properties are going to depend on these numbers. So this is the process of modulation. The carrier will carry the information, but also be adjusted to the properties of this channel. It can be baseband, or it can be passband, depending on the type of the transmission. Now this is our channel, and we assume that this is AWGN, so there's going to be some noise over given properties that is added to the signal. Now here is where we need to do recovery of digital information. And if we did everything right, the same numbers that were sent here are actually appearing over here. So this, if I send one into this thing, it will map this one onto analog waveform. This analog waveform will travel through the channel. There will be some processing here, and one will come out. as a result of the communication system. Now here I have to do an inverse process, digital to analog conversion. And then there will be an information sink here, right? That is at the end. Subject of our study is going to be from here to here. We're going to assume that we're given a bunch of numbers, and we have to devise the system to produce the same numbers at the output here. Now, these numbers are usually ones and zeros in communication because we work in a system of two. So we're going to focus, how do you take ones and zeros from this side and deliver them to ones and zeros on this side? In order to attack this problem, we actually have to do some math, introduce some tools that we need. And not surprisingly, we'll learn to look at these signals in yet another domain. Remember, we had time domain, we had frequency domain. Now we're going to have actually two more domains. One is going to be signal domain, and the other one is going to be a vector domain. And we need to kind of learn what they are. And then later on, you will see that it simplifies tremendously the way how we see things in the digital world. If we have time, we can stop and look what we have done so far in terms of these two domains. And you can see that we've been using them all along. We just didn't call them that way because we didn't want to introduce additional terms and additional complexities. But what we're going to be doing here is going to be very, very familiar. And it's going to be very comparable to what we did with analog signals. So let's talk about the geometrical representation of signal waveforms. Of signal waveforms, or signals in general. So here's the setting. We have a certain interval in time, right? This is from A to B. I'm going to call this an interval I. And this interval has a duration of capital T. T is what we're going to later define as a symbol time, or the period over which you're doing your signal. On this interval, we're going to define a bunch of signals. This is S1 of T. This is a signal S2 of T, and so on. We can have M different signals. So there are M possible on interval I. To not be so abstract, what is it that I'm talking about here? Well, let's assume that you're going to have some numbers that you're trying to send from one side to the other. In the most simple case, it's going to be two of them, 1 and 0. Okay? So the way how we're going to do this transmission, we're going to take in the most simple case 1 and find a waveform that will attach to 1, let's say plus pulse. And we're going to have 0 and find a waveform that we attach to 0 and send that on the other side. So that's the simplest possible scenario. I have two possible numbers. I can pick two possible waveforms for my transmission, right? In general case, what we, however, do is we combine multiple bits at a time. Therefore, you get multiple possible numbers. If you combine, let's say, 2 bits at a time, you have 4 possible numbers, 0 to 3. If you combine 4 bits at a time, you end up with 16 possible numbers. Therefore, you may need up to 16 different waveforms that you're going to define on this interval. And then, depending on which number comes in, you're going to pick one of these waveforms and send it to the other side. Right? So that's the settings. That's where this all is coming from. I'm not just saying, let's invent some signals. This is quite real. Now, what we're going to learn here, so this is our work. This is time domain. Or I can call this also signal domain. That's the world that we are in. We're going to define an alternative world in which here's what's going to happen. I'm going to have some coordinate system that we're going to discuss, and you will see that most of the time it's either just one-dimensional or two-dimensional, but in general it can be of any dimension, where these waveforms are going to be mapped into a vector. So in this coordinate system, I'm going to have a vector S1 that is going to be a vector that corresponds to this S1 of t. And then there will be a vector S2 that corresponds to this signal here, and so on. There will be a vector Sm that corresponds to this vector, to this signal Sm of t. So we need to devise this mapping here, right? And you will see a little bit later how we do that. What is going to be a benefit of this? Well, just like if you remember what we did when we defined the Fourier domain and a spectral analysis for the analog signals, we discovered if we stayed in a time domain, we have to do differential equations. And that's how this world is governed, through the differential equations. When we switched to frequency domain, the convolution and differential equations become algebraic equations. It becomes simple multiplication and division in a frequency domain. It simplified our math. It also provided us with some very valuable insight how things work. The same thing is going to happen here. You will find out that if we were to stay in this domain, we would still have to do a lot of calculus. There will be a lot of integration, a lot of differentiation, and so on. Once you switch to this domain, those integrals become just dot products. They become much simpler operations to do. So a lot of times, but that's not the only benefit. Even bigger benefit is going to be clarity with which we're going to explain things in this domain. So we're going to be switching between these two domains. They're going to represent the same things, but sometimes I'm going to stay in this domain, especially when I talk about how you realize certain things practically, because we live in this domain, all of our equipment is in this domain, so it has to do these operations. But explanation and the view of what is actually happening and the reason why we approach certain things a certain way, well, would be usually much more clear in this domain. Okay? So we need to figure out now, how do I go from this domain into this domain? How do I devise some sort of transform? And to do that, what I need to define first is something that is called dot product between two functions. You understand from, God knows when, from high school, what the dot product is between two vectors, right? So you're kind of familiar. You take the magnitude of the first, magnitude of the second, times the cosine of the angle between them, right? Or if you're given them coordinate by coordinate, it's the first coordinate times the first coordinate plus the second, and so on. So here we have to define something a little bit similar, but a little bit more advanced. Is if I have a bunch of functions, how do I take a dot product between two functions? So let's define that. Definition of dot product between functions. So consider functions as I of t and as j of t defined on interval I. The dot product is defined as, and this is the notation that I'm going to use, as I of t in dot product with sj of t. So I'm going to use these I don't know how you call them, triangular brackets. This is integral over this interval I Si of t times Sj of t complex conjugate dt. So you take the first function, you multiply it by the complex conjugate of the second function, and you integrate over interval I. Now, in our case, in this case, or in the case of this class, Si of t and Sj of t are always going to be real functions of time, right? So if Si of t and Sj of t are real functions, then the complex conjugate of a real function is the function itself, and you end up with Si of t times Sj of t is equal to integral over I Si of t times Sj of t dt. All right. So I just have to define it properly, because this is how we define this properly in telecommunications. In our case, we're going to switch to a much simpler, or to a simpler definition. But remember that this was, you know, we're not going to need this one in this course, but in general, when you read books and papers on these subjects, this is how they treat dot product. So let's look at some properties of this dot product. A lot of these properties are just easily proven from definition. I'm not going to prove all of them. Some of them will be just straightforward to see. If it's a little bit more complicated, then I'll see if I have a proof here. But first one is this one. Si of t in dot product with Sj of t is the same as J of t in a dot product with Si of t. And you can see that this is the case. Why? Because if you look at the definition, that integral over there, it really doesn't matter who comes first and who comes second. It's the same thing for real functions Si and Sj. The second property is let A be a real number, then A times Si of t in dot product with Sj of t is the same as the dot product of Sj of t. This is called association with a scalar. Again, if you put this as an integral, then you know that you can bring the constant inside the integral. So it's very straightforward to see this one. The third one is distributive property. It says that Si of t in dot product with Sj of t plus Sk of t is the same as Si of t in dot product with Sj of t plus Si of t in dot product with Sk. Right? This is distributive property. It's very easy to prove, so just as an illustration, let's go to a proof of this one. So let me just write a proof. Si of t in dot product with Sj of t plus Sk of t, by definition, is an integral over this interval I, Si of t multiplying Sj of t plus Sk of t dt. And now you can see you can split this integral into two integrals. So this becomes integral over I Si of t times Sj of t dt plus integral over same I Si of t times Sk of t dt. But if you look at what this first integral is, this is nothing but the dot product between Si and Sj, and this is the dot product between Si and Sk. So this is Si of t times Sj of t plus Si of t with dot product of Sk of t. Okay? So that's these are some of the properties that we're going to be using. Let me define two other things. So to give you two definitions. First one is definition of a signal norm. We define the norm of the signal Si of t as you take Si of t with dot product with itself, and then you take the square root of that. Okay? Now think about, whenever I write something here in the signal domain, do this exercise. If Si was a vector, how would I define its norm? The length of the vector. How do I define it? Its magnitude. How can I calculate it? I take the vector in dot product with itself, right? And then take a square root of that, right? And that gives me a norm, gives me the length of that vector. So I'm following the same approach here. I take my signal in dot product with itself, and I take the square root of that, and I define it to be norm. Now, you can see the definition of this is integral over I, Si of t, times Si of t. So that's this thing, and then I have to take a square root of that. Now, this thing underneath the square root is a good friend of ours. What is this? For a given signal. If I take a signal and I square it, and I integrate the area under the curve, it's not power, it's something is missing for this to be power. But you're on the right track. If I take the signal and square it, an area under the curve is what? It starts with E. Energy. This is energy of the signal, right? If I divide by the time, then I get average energy over time, which is power. But this is just an energy of the signal. So we can see that physically, what the norm of my signal is going to be square root of energy, right? But strictly speaking, what is norm of the signal? You take the signal, dot product with itself, and take the square root of that. And that's some level of magnitude that we attribute to a signal. And it makes intuitive sense that the signals with larger energy have larger magnitude, right? The signals with small energy have small magnitude. So that's how I define the signal norm. And then I define the concept, definition of orthogonality. When do I say that the two vectors are orthogonal? What needs to be, don't tell me if they're perpendicular, right? Tell me what happens to them in terms of the dot product?
The dot product should be 0.
Should be 0. So if the two vectors are orthogonal, their dot products is equal to 0. So if I have two signals, Si of t and Sj of t, I'm going to declare that these two guys are orthogonal if Si of t in dot product with Sj of t is equal to 0. Okay? So that's how I define the orthogonality. And then another thing that I can define is linear independence. Let me just give that definition. And then we have all the tools we need. So consider M signals defined on interval I. This is a linear combination. Which I'm going to say it's A1 times S1 of t plus A2 S2 of t, plus and so on, plus Am Sm of t is equal identically to 0 for every t, right? Yeah, I should say here, if linear for some non-zero Ai's, where I goes from 1 to n, the signals are linearly dependent. Otherwise, they are independent. This is a long definition for something, for a concept that is very, very easy to understand. You have m signals. Can I pick one of the signals in that group and express it as a linear combination of the others? Let's say I have 3 signals, and the third signal is 2 times first minus second, right? Then the third signal can be expressed as a linear combination of the first 2. If that is possible, then these signals are dependent, right? Because I can express some as a function of the others. If that is not possible, then I cannot. Then these signals are independent, right? And you cannot express one as a function of the other. So if you have a set of m of them, it is possible that the set contains independent and the ones that are dependent, right? The number of independent ones that you have in a set is called the size, the basis of the set, the size of the basis of the set. And again, always look this in terms of the vectors. Let's say if I'm looking all the vectors in a plane, right? Everything is in a plane. How many independent vectors can I have on a plane? 2, right? If I have this, I can have m vectors, right? These are all of my vectors, right? S1, S2, S3, S4, S5. But I can express all of these vectors in terms of these 2, I and j, right? So the basis of this space is n equals 2. I have 2 basis vectors, and I can express all of these as a linear combination of these 2. So these 5 vectors are always going to be linearly dependent. I can only have 2 vectors that are linearly independent. So suppose I give you a set of m vectors. So this is a question. Consider a set of m signals on the interval I. Then how do I determine the size of the basis for this signal set? How many linearly independent signals I have in this signal set? So let me just not make this question. So the size of the signal set basis may be determined through a process called Gram-Schmidt orthogonalization. Okay, so what is the objective here? I have m signals defined on integral I. How many independent signals I do have, right? What is the minimum signal set that will allow me to express all of these signals by manipulating just these 2? Why is that important? Let me give you some analogies so that you kind of start seeing where we're going with this. You know that we have infinitely many colors, right? If you look at, well, maybe not infinitely, in computer world, you always have a certain number of colors. Let's say you're going to have 16 or 64 or 32 and so on. And these are the distinct colors that we decompose all of our images along these colors, right? But how many colors do we have to build all of these colors? How many? 3. So it can be shown that we can build every color on a TV screen or a computer screen by combining red, green, and blue, right? So red, green, and blue are going to be basis vectors, and every color that I build is going to be a combination of red, green, and blue, right? So if I give you a set of a whole bunch of signals, let's say I give you on an interval, give you 15 signals, I'm trying to answer the same fundamental questions. Okay, I have 15 signals, but is there a smaller subset that I can use to represent these signals, right? And why is this important? Because when I transmit, I'm not going to transmit these original 15 signals. What I'm going to try to transmit is 3 signals that decompose these 15 signals. That way, I need to worry only about 3 signals every time. And I would reinterpret my color at the end as a mixture of these 3 signals, right? So I'm always trying to decompose whatever I need to send into more elementary pieces. And this is going to be, these are going to be my basis signals or my basis vectors. So the question is, if I'm given 15 signals, is there a systematic way for me to determine the basis vectors and the size of the vector space? And the answer is yes. And that methodology is called Gram-Schmidt orthogonalization. So that's the systematic process that you can work through the signals that you're given to determine the basis of the signal set, to determine how many basic colors you need to represent all the colors in this signal set. So let me spell out how does this orthogonalization process work. And then I'll give you a couple of examples that illustrate this more tutorial. So, Gram-Schmidt orthogonalization. The input here is your signal set Sm of t, where m goes from 1 to some capital N, capital M, sorry. And you're trying to find out a new set of signals, which I'm going to call psi I of t, where I is going to go from 1 to n, where this n is always going to be smaller than m, right? And these signals psi I needs to be such that you can pick any signal from this set and express it as a linear combination of the signals from this set, right? Pick any color here and express it as a linear combination of the colors here, right? So how do I determine this psi I? So let's look at, it's an iterative process that has several steps. In the first step, I'm going to say psi 1 of t is going to be S1 of t divided by square root of energy 1, where this energy 1 is going to be integral over I S1 square of t dt. So I pick an arbitrary signal as a starting point, and I say, okay, let me pick this first signal and make that my first basis vector, right? And I'm gonna, through this process, you also see that what I'm doing is I'm making every one of these psi i's of a unit norm, right? They're gonna be unit length vectors. They're not gonna be, they're all gonna have the same norm. In the second step, I'm going to say, okay, d2 of t is going to be s2 of t minus s2 of t times psi 1 of t times psi 1 of t. And then I'm going to make psi 2 of t equal to d2 of t divided by square root of energy 2, where this energy 2 is equal to integral over I d2 squared of t dt. So what is the thinking here? Well, I'm going to take this next one in line, which is S2 of t, and first I'm going to project S2 of t along the direction of psi 1 of t. When I say project, you remember what that means in vector domain. You take the dot product between the vector and the coordinate vector, right, with I. And I'm going to take whatever I get multiplied by vector psi 1 and subtract that from S2 of t. So what is left here after I do this has to be orthogonal to the direction of psi 1 of t, right? Why? Because I took whatever projects from S2 of t along the psi 1, and then I subtracted that from S2 of t. So whatever is left, there's nothing that projects on psi 1 anymore, right? So whatever is left is orthogonal to psi 1. So I take that as a new vector, and I normalize it, and I call that as psi 2 of t. So you can see by the construction, two things happen. Psi 1 and psi 2 are of a unit norm. Why are they of the unit norm? Because I normalize them to their energy, but also they're mutually orthogonal, right? Because psi 1 is formed from S1, and psi 2 is formed from S2 portion that is orthogonal to S1, right? And then you keep on doing that. In a kth step, you're going to define dk as sk of t minus sum when I goes from 1 to k minus 1 sk of t projected on psi I of t times psi I of t. So that's going to be your dk of t. And then you're going to define psi k as dk of t divided by square root of ek, where ek is an integral over I dk squared of t dt. So at every kth step, you would take kth vector from this set here. You take projections of this vector on all the basis vectors that you have already extracted, and you subtract that. Whatever is left has to be orthogonal to all the previously extracted vectors, and you take that and you normalize it and you call it your new basis vector. So by doing this, you're going to actually find out a set of psi k's that are mutually orthogonal. They have a unit norm, right? And then you can express every one of these vectors as a linear combination of these psi k. So to explain how this process works, I have an example here. But before I go into example, let me sketch really geometrically what is happening here. Let's say I'm given 3 vectors, S1, here's my next vector, S2, and here's the third one, S3. And I'm asked to find out my psi 1, psi 2, and psi 3. So let's say all this x and y. What is psi 1? I take S1 and I normalize, right? So I divided it by its norm. So I'm going to end up with a vector that is in the direction of S1, but it's going to have a unit norm. So this is my psi 1, right? That's the first vector. The second vector, I take my S2, I project that to the direction of psi 1. So this here, this vector is S2 in a dot product with psi 1 times psi 1, right? This vector from here to here, okay? And then I subtract that from S2. So what do I end up with? I end up with this vector, right? So this is my D2. You see that? This thing here is D2. So how do I form psi 2? I take the D2 and I divide it by its energy. So I normalize it, make it a unit vector. So here's my psi 2. Okay? So that's the two vectors that I have extracted. They're both of a unit norm. They have a unit length that came from the normalization. And they're mutually orthogonal. Why they're mutually orthogonal? Because when I was forming psi 2, I subtracted everything of S2 that was along the direction of psi 1. So it had to be, what it was left was orthogonal to psi 1. Now I take S3 and then I try to find the third vector. But I take S3 and I project that to psi 1. So this is this part. Take S3 projected of psi 2. If I take S3 and as I subtract this vector and I subtract this vector, what do I end up with? 0, right? So at this point, I discovered that n is equal to 2. I have two vectors, psi 1 and psi 2. And then all of these three vectors that I have can be expressed as a linear combination of psi 1 and psi 2. Psi 1 and psi 2 form the basis of the space, and the size of the basis is n equal to 2. Okay? So this is what I'm doing, right? In vectors, it's really easy to understand. The same thing essentially happens here, and I'm going to go through an example to show you how this works with signals, right? So let's consider 4 signals, and we're going to try to find out the basis for this space. So let me look at an example. T, the interval is the size of 3. This is my signal S1 of t. And this is how this signal looks like. And this is the signal S2 of t. 1, minus 1, 1, 2, 3. So this is S2 of t. Then this is the signal S3 of t. 1, 2, 3 as a function of t. This one looks like this. This is 1, this is minus 1. And then the last one, S4 of t, is just like this. Right? So, how large is n? In this case, I is an interval between 0 to 3. How large is n? Capital N. That's the size of the number of signals I have in my signal set. What is it? How large is n? No. 4, right? 1, 2, 3, 4, right? M is Sm of t. M goes from 1 to capital N. So I have 4 signals in my signal set. And the question I'm looking for is, how large is n? How large is n?
N?
Yeah. How do you know?
Is it 10?
10? No. It cannot be larger than n. All I know is that n needs to be smaller than n. N is the number of basis vectors, so it cannot be larger than n. If these guys are all linearly independent, then n is equal to m. But if there's a dependency between them, n is smaller than n. The question is, I have no idea. At this point, you have no idea, right? The answer is going to be obtained by systematically going through the Gram-Schmidt orthogonalization, right? So at this point, you don't know, right? Not everything you can guess, right? So let's just go through the process and we'll find out what the end, and in the process is, as we execute this process, we're also going to find out what these psi's are. We're going to find out, and we'll hopefully find out how each one of these can be expressed as a linear combination of the psi's. So for the first one, it's easy. So here, I'm going to say energy 1 is integral from 0 to 3 s1 squared of t dt. So what is this energy? If I square s1 of t and I integrate it from 0 to 3, what do I get? Look at this thing. If I square it, you can do that in your mind. Square it and tell me what the area under the curve is. 2, right? 2. So the energy of the first signal is 2. So psi 1 of t, that's my first basis vector, is going to be 1 over square root of energy times s1 of t. So that's my first basis vector. Let's look at how do I extract the second one. The second one, I have to form d2 of t. And d2 of t is s2 of t minus s2 of t projected to psi 1 of t times psi 1 of t. So I have to take whatever is the signal s2, project that to the extracted vector psi 1, and subtract that part from the s2. So whatever I get is going to be orthogonal to psi 1. So now, if I, first let's take s2 of t times in dot product with psi 1 of t. By definition of dot product is going to be integral when t goes from 0 to 3, s2 of t times psi 1 of t dt. In our case, this becomes integral when t goes from 0 to 3, s2 of t times 1 over square root of 2 times s1 of t dt. Where is this coming from? Well, our psi 1 was this. So this is an integral from t goes from 0. Now if I look at here, both of these signals actually exist only between 1 and 2. So I need to integrate between 0 to 2. And then actually I need to integrate between 0 to 1. And it's going to be 1 times 1 over square root of 2 times 1 dt plus integral when t goes from 1 to 2, 2, or actually minus 1 times 1 over square root of 2 times 1 times dt. Why is 1? Because here s2 of t in this interval is equal to 1. And here s2 of t is minus 1 between 1 and 2, right? So just multiplying and integrating, you know, by sub-intervals then. So what is the value of this integral? Well, this is 1 times 1, 1 over square root of 2. Integral from 0 to 1 dt is 1. So this is 1 over square root of 2. Okay? So this is 1 over square root of 2 minus 1 over square root of 2 is equal to 0. So we luck out here. S2 in dot product with psi 1 is equal to 0. So what can I say about these two? If their dot product is equal to 0, they are orthogonal. So S2 is orthogonal to, already orthogonal to psi 1. So I can form my psi 2 as just S2 of t divided by energy, square root of energy 2. What is the energy of this signal? If you square it and integrate the area under the curve, 2, right? So the psi 2 is going to be 1 over square root of 2 times S2 of t. So I already extracted 2 of them. So n is at least 2, right? Okay? Let's see if n is larger. Let's see if we can get another one. Another that is going to be orthogonal to psi 1 and psi 2. So in a step 3, I'm going to form D3 of t as S3 minus S3 of t minus S3 of t in dot product with psi 1 of t times psi 1 of t, and then minus S3 of t in dot product with psi 2 of t times psi 2 of t, right? So I'm taking S3, taking a dot product with the previously two extracted vectors and searching for the part of S3 that's not along the directions of psi 1 and psi 2, which is orthogonal. Now you can show easily that this holds. S3 of t in dot product with psi 1 of t is equal to 0. But S3 of t in dot product with psi 2 of t is equal to minus square root of 2. Okay? How do you do that? You actually, just like I did it here, you multiply the 2 and then integrate over the integral. So now I see that D3 of t is going to be equal to S3 of t plus square root of 2 times psi 2 of t. That's my vector D3 of t. Let's see how does this guy look like. Well, D3 of t, you take this guy, S3, you take square root of 2 times psi 2. Well, psi 2 is 1 over square root 2 times S2. So when you multiply by square root 2, you actually get S2 of t. So what this says, take S3 of t and add S2 of t. So take this one and add this one. How does this one look like? If you take S3 of t and you add S2 of t, what do you end up? You end up with just the square pulse between 2 and 3. So this is it. So the norm, E3, is going to be integral from 0 to 3 d3 squared of t dt. Well, what is this? If you square d3, d3 is S3 plus S2. That's just that square pulse between 2 and 3. If you square it and integrate, what's the area under the curve? 1, right? It's already unit 1. So our psi 3 of t is going to be S3 of t plus square root of 2 times psi 2 of t. Okay? So that's our third vector. So n is at least 3, right? So we have extracted. Let me actually draw these 3 so that you can see what they look like. So psi 1 of t looks just like this one, but divided by square root of 2. So this is 1, 2, 3, and its magnitude is 1 over square root of 2. Psi 2 of t looks just S2, but it's divided by square root of 2. So it looks like this, and the magnitude here is plus 1 over square root of 2. And magnitude here is minus 1 over square root of 2. So this is psi 2 of t. Psi 3 of t looks like this, where this magnitude is 1. So these are the 3 vectors that I have extracted so far, right? Now the question is, can I use this one to get psi 4? So I apply now, this is the 4th step. I say something like this: d4 of t is going to be s4 of t minus sum, when k goes from 1 to 3, all the previously extracted vectors. I take s4 of t in dot product with psi k of t times psi k of t, right? That's my whatever is orthogonal to the previously extracted vectors. If you take these dot products, here's what you get. S4 of t with psi 1 of t is going to be square root of 2. S4 of t times psi 2 of t is going to be equal to 0. And S4 of t in dot product with psi 3 of t is equal to 1. Okay? So now, I look at what is d4 of t. So d4 of t is going to be equal to S4 of t minus square root of 2 times psi 1 plus 0 times psi 2 root of t plus 0 times psi 2 of t, and then minus 1 times psi 4 of t. So I have to take this signal here, S4 of t, and subtract square root of 2 times this one and 1 times this one. What do I end up with? Take this signal here, S4 of t, and take this signal here, multiply by square root of 2, and subtract from it, right? This minus square root of 2 times this, and minus this. What do I get? 0, right? So d4 of t is equal to 0. So what do I know then? I know that my S4 of t can be seen as square root of 2 times psi 1 of t plus psi 4 of t. So S4 of t is not linearly independent. The S4 of t can be expressed as a linear combination of these three. Okay? So also, it's very easy to see S1 of t is equal to square root of 2 times psi 1 of t. S2 of t is equal to square root of 2 times psi 2 of t. And S3 of t is equal to minus square root of 2 times S2 of t plus psi, not S2, plus psi 2 of t plus psi 3 of t. Okay? So, I have, how large is my n? What's the answer? N is equal to what? 3. N is equal to 3. And I have here expressed all of my 4 vectors as a linear combination of these 3 basis vectors. What I really prefer as a notation is to do this. Write this as square root of 2. What is this? Cannot be 4.
It's supposed to be 4?
3. It's supposed to be 3, right? Because there are no, right, 3, right? There are no 4. So it's square root of 2, 0, 1. This one is just square root of 2, 0, 0. This one, 0, square root of 2, 0. And this one is 0 minus square root of 2 and okay? So now you can see how I transition between the signal space and actually assign the vectors here. Right? And these are now 3-dimensional vectors where every one of these vectors has a corresponding waveform. Okay? So that's, any questions here? Okay. So what we're going to do is, how does this tie to our digital communication? In digital communication, we're going to define certain basis vectors. And they're not going to be this arbitrary. They're going to be usually sine, cosine, or something that we pulse, or something that we like to use for signaling. Depending on how large n is, we're going to be talking about 1-dimensional signaling, 2-dimensional signaling, 3-dimensional signaling, and so on. And depending how, but in any case, let's say you use two-dimensional signal, you can create an arbitrary many signaling vectors, S's, as a linear combination of your basis vectors. So we're going to have n symbols in our signal set that will be created out of n possible basis vectors. Right? So that's the approach that we're going to take. And you will see much more of this, but the reason why I'm kind of saying all of this, because I don't want to lose you on these abstract things. I want you to see that this is actually what we're going to be doing, right? So don't sleep through this part. Okay, so two more things. I want to look at now that I've defined these vectors. I have two things that I want to actually look at. One is I define my norm in a signal domain. Well, what does that translate into vector domain? Can I calculate the norm of these signals from the coordinates here? And then I want to see, well, if I have a dot product in the signal domain, what does this correspond to in a vector domain, right? Because right now what I did, I took my signals and I found the vectors for them. But I have norm on this side and dot product on this side, which I've clearly defined. Dot product is that integral over I Si of t times Sj of t. So what does that correspond to in this domain? And then I have a norm here, which was Si of t in dot product with Si of t taken square root of that. What does that correspond to in a vector domain? So let's look at those two things. So norm or energy. Let's look at what the energy is. How does the energy map between signal domain and vector domain? So let's say the energy of signal Sm of t, right? Let me call it Sm. How do we define the energy? It's Sm of t in dot product with Sm of t, right? That was the energy, or in other words, this is an integral of the magnitude of Sm of t squared dt. But I know that this is an integral over I, and I can take my Sm of t, and I can write that as n goes from 1 through n, Smn times psi n of t. What am I doing here? I'm saying, well, I can take my Sm of t, and I decompose it as a linear combination of my basis vectors, right? That's this, right? I can take S1 of t and S4 of t, and I say, to get S4 of t, you need the square root of 2 of psi 1 plus 1 times psi 3 plus 0 times psi 2, right? So this is what I'm saying here. I can take my Sm of t and I decompose that as my mixture of my basis signals here, right? What are these numbers Smn? How do I determine these numbers?
This one is 2 is 3.
Huh?
If the sequence S1 is 2 is 3 numbers.
But what is this number here? What is Smn? What? It's what?
The number.
The number. How do I get it? How do I get that number?
Is it the coordinate?
Is it the right column? No, the right. Look at it here. I project my signal onto the basis vector. When I say project, I take the dot product. So these SMNs are really Sm of t dotted with psi n of t. Right? That's a coordinate. right? Coordinate is a projection. Coordinate is a dot product between your vector and the basis vector, or in this case, between your signal and basis signal, right? So this is how I decompose it. So now, if I take this one step further, well, this is an integral over I. This thing here I can write as sum when k goes from 1 through n, Smn squared psi n squared of n, plus all the cross terms, so 2 times sum when k goes from 1 through n, actually no 2, sum when k goes from, or rather p goes from 1 through n, where k is different than p, Smk Smp times psi k of t times psi p of t. Right? Little bit d. What is it that I'm doing? I'm just squaring here, right? So it's the first one squared plus 2 times the second one squared plus and so on. But if you have all of them, then you just extract all of the like ones and all the different ones. Right? Now this is very easy to integrate. Let's just switch the orders of the summation. So this becomes sum k goes from 1 to n, Smn squared integral over I psi n squared of t dt, and then plus sum k goes from 1 to n, sum when p goes from 1 to n, but p is different than k. What happens when p is equal to k? That's this one, right? I already put it outside. And then Smp times Smk integral over I psi k of t times psi p of t. Now, what is this? This is a norm of my basis vector. What is the norm of my basis vector? By construction, I made it what? What did I make it by construction? Remember this normalization? I erased it, but by construction, I made sure that these psi's have unit norm, right? So this integral here is equal to 1. 1. This is a dot product between what? Between two basis vectors. What's the dot product between them? 0. Why? Because by design, by how I extracted those, I made sure that they are orthogonal. So their dot product is equal to 0. So this ends up being sum when k goes from 1 to n, S m n squared. Now look at this, how beautiful this is. What is this? If I have a vector and I take all of its components and I square, this is a square of the distance from the origin, right? So the energy in a signal domain corresponds to the square of the distance of the vector from the origin. Norm of the vector in a signal domain, which we define as a square root of energy, corresponds here to distance of the vector from the origin. Well, guess what? This is what we call norm in a vector domain too, right? So the norm in a signal domain, the way we define it, translates into a norm in the vector domain for all of these vectors that correspond to signals, right? So that's a beautiful result. It doesn't have to be that way, but we were careful with our definitions, so it ends up being that way, right? So the norm in the signal domain and norm in the vector domain, they end up being the same thing. And the last thing, let's take a look at now dot product. Let's have Sm of t is going to be mapped into Sm1, Sm2, all the way to Smn. Right? This is now the vector that corresponds to this Sm of t. How do I determine these? As dot products between Sm of t and the corresponding psi, right? And let's look at Sn of t. Let's call it P. Sp of t as Sp1, Sp2, Spn. Now this is a vector that corresponds to this other signal Sp of t. If I take the dot product in a time domain, Sm of t, in a dot product with Sp of t, by definition this is an integral over I, Sm of t times Sp of t dt. But I can rewrite this as an integral over I, sum when n goes from 1 through n, Smn times psi n of t. What is this? This is the representation of Sm of t as a linear combination of my basis vectors psi's, right? I can do that, where these are now dot products with Sm and the corresponding psi's. And now I can say, well, times sum when nu goes from 1 through n, Sp nu psi nu of t dt, right? This is now the expressing of Sp of t as a linear combination of my basis vectors. So let me now reshuffle this a little bit. So this becomes sum when n goes from 1 through n, Smn times Sp nu integral over I psi n of t times psi nu of t dt. Well, what is the value of this integral? Well, it depends what p and nu are. If p is equal to nu, what's the value? 1. If p is different than nu, 0. So even though I have a double sum here, which I forgot to write, nu goes from 1 to n, even though I have double sum, it is really only having terms when nu is equal to n, right? So I can write this as sum when n goes from 1 through n, Smn times Spn integral over I psi n squared of t dt. What's the value of this integral? 1. So this is equal to sum n goes from 1 through n, Smn times Spn. What a beautiful result. The dot product of two signals gives you the same result as the dot products with their corresponding vectors. Right? So we have now a complete analogy between two worlds. You know, we have the signal world where I have to deal with these time waveforms, and when I have to take the dot product, I need to integrate. And then I have the vector world in which I'm not dealing with the time domain functions, I'm dealing with vectors. And if I look at for norm, I look at for the distance from the origin. And if I look at for dot product, it turns out it's just the dot product with those two vectors. So that's the end of the this mapping business. So let me just take 1 minute and summarize what we learned today. So we start with a set of signals that I define on this interval from A to B that I call I. And there's going to be M of these signals. This is S1 of t, S2 of t, Sm of t. This is what I call signal space. Then I'm going to define another world where I'm going to map these signals into vectors. These are going to be psi1, psi2, all the way through psi n. And these signals are now going to be points here. So this is a vector S1 that corresponds to signal S1. This is a vector S2. This is the vector Sm that correspond to appropriate signals in this signal space. This is what I'm going to call vector space. Right? Now, Sm as a vector is going to be having coordinates Sm1, Sm2, Smn, where each one of these coordinates, Smi, is going to be determined as Sm of t in a dot product with psi I of t. Right? That's determined in a time domain, or if I want to expand, it's going to be integral I Sm of t times psi I of t dt. The dot product in a time domain, Si of t, in dot product with Sj of t, is going to be Si transpose times Sj, where Si and Sj here are the vectors that correspond to the signals Si of t and Sj of t. The norm of Si of t is going to be the same as the norm of Si, because remember, we define the norm as the distance from the origin. So the magnitude of the vector is the same as the norm. And then we also claim, so this is the first thing, the second thing, and the third thing, Si of t in dot product with Sj of t is equal to 0. That means that Si transpose times Sj is equal to 0. So if these waveforms are orthogonal in a time domain, their vectors are also orthogonal in a vector domain. Okay? So orthogonality kind of stays in both domains. Let me give you homework. This is number 15. Exercise none. And I have assignment. These are from the textbook 7.3 and 7.8. Okay. Let's take a little bit of break and then we'll start using this. I have